stress, guys. Tau. Forgive my handwriting, guys. I'm getting used to it. Now let's go back to the relation. Tau over r is equals to T over J. Let's bring out these two. Not that you can't use any other bone. Let's bring out these two. I am T tau over r is equals to T over J. So now tau is equals to T times r over J. Guys, remember this is your torque, this is your radius of wire, and this is your polar moment of inertia. So it means that now, of course, torque, we also know that the dimension is Newton meters. When we did MEG, it was, what was the formula in our mechanical? We did a course on mechanical engineering where we use RS Kumi for our textbook. Yes, let me remember. Torque is equals to W times D over 2. Yes. This is it. But regardless, the unit is, sorry guys. Regardless, the unit is Newton's meter. So yeah, torque is WR. So substituting it inside this equation, we'll be having WR. Note the term R here. This is the radius of coil and not the radius of wire. This other R here is the radius of the spring wire over J. So now stress is equals to WR times D over 2 divided by J is pi D4 over 32. Note once again, this D I'm using is the diameter of the spring wire and not the coil. These guys, these notes, and watch out for this. So WR times D over 2 times 32 over pi D raised to power 4. 2 cancel here, leading to 16, leading to 3. Then we have that our shear stress is equal to 16 WR over pi D cube. Equation 1. The first fundamental equation we need. So let's move to deflection, guys. Who's excited? Deflection. Let's move to deflection. A minute, guys. Just a minute. Just a minute. Just a minute. Just a minute. So now, back to our torsion relation. G theta, that is G times our modulus of rigidity times our angle of twist over L is equals to T over J. Let's bring out this. Let's use this rather. No, there were 3, of course. Is equals to. Now, from this equation, we can say that angle of twist is equals to TL over JG. And we can say that TL is equals to WR times length. Length is equals to 2 pi Rn over JG. We can say that, okay, theta now is equals to 2 pi R square Wn over G times, when you take this polar moment of inertia, you invert it, it gives you 32 over pi d4. Then eventually you have 64 pi r square wn over g pi d4. Pi cancels out. You'll be having 64 r square wn over g d4. Now, but remember from what we just said about our triangle, that's this. So therefore this is equals to 64 r square wn over g d4 times r, which is equals to 64 r cubed wn over g d4. Stiffness. Now we know that the stiffness dimension is Newton per meter. So basically, force over deflection, or rather the load applied, the gradual load applied to the spring over the deflection of the spring. So I can say that K is equals to W over deflection. And if we look at it, we've derived the formula for deflection. Please, for courses like this, I would recommend that you will know how to derive the formulas, and you know how to store in your formulas. That is, you derive your formulas when it calls for deriving. That is, maybe probably you're hacks in the exam, or probably you want to explain to someone, or rather you just remember your formulas. Maybe you are solving a problem in your exams and you have to be fast. You can't be deriving, so you need to know how to remember. So remembering the formula for deflection, 64 W R cube and over G D4. Yes, I remembered. So K is equals to W times G D4. That is basically W over deflection. So when you do the maths, you get this. W cancel W. The stiffness of the spring leaves us to this. 64 R cubed N. Yes, guys. So let's move to the Wahl's correction factor. This is spelling. Okay, I think so. Wahl's correction factor. Let me get the best angle. Yes. So I want you to note one important thing. Earlier, when we derived the formula for the shear stress, we derived the formula which is tau. We derived the formula for deflection. I want you to know that even this stiffness that we just derived, I want you to know that we didn't include, or rather we neglected the effect of bending. And we also neglected the effects of shear stresses. But Wahl's correction factor is now here to introduce the correction. That is, it is here to include the bending, it is here to include the shear stresses. However, it only applies to the shear stresses. The lucky guy. Someone getting what I'm saying? So, once again, remember, you have to remember when it calls for remembering, and you have to derive when it calls for deriving. Shear stress is equals to 16 WR over pi d cube. Shear stress. So what Wahl's correction factor will now do is we'll times it by itself. By timesing this shear stress expression by the Wahl's correction factor, it means rather that the shear stress now includes the bending effect and the shear stresses effect. Do you get what I'm saying? So now, what is this Wahl's correction factor? It has a formula. It's equals to God help me, 4s minus 1 over 4s minus 4 plus 0.615 over I think s. Yes, s. I'll just confirm it, s. So this is the formula where s is equals to your diameter of coil over your d. S is called spring index. This is diameter of coil, diameter of wire. So I want you to note something. When you are solving questions with this, don't include the Wahl's correction factor unless it is asked for you to include it. And how do they now ask you to include? The question might say, okay, including the bending effect, including the shear stresses. That's when you include the Wahl's correction factor. Or the question can just say, find the shear stress, find the shear stress using the Wahl's correction factor. Then that's when you use it. However, if it doesn't say it, if the question that you're solving or you are dealing with didn't specify you to use the Wahl's correction factor, don't use it. Just use what we have derived earlier. Just use what we have derived earlier.